figure out momentum or something like that.
You don't need to. None of that's important. We can do
Well,
this.
like when you're pulling a boat in.
You're not actually doing this, Rose. This is like a on-paper problem. It's not something you're gonna go out and do.
He told us to think about real life too.
Well, okay, but this is, I mean, and when you're drawing your picture, right? But this is, yeah, don't, on problems like this too, you wanna make sure that you're taking a position in your approach to the problem that's gonna be based very precisely upon the information that's given to you, right? So we can't make any assumptions here about slowing down. I mean, we can't, right? We can't introduce any emotional elements here. I mean, this has just gotta be just the facts, man. Okay, so let's draw this picture, right? So we've got our boat floating on, and we can maybe, it doesn't need to be a fancy picture, but I just can't help myself. I'm such a good artist. Not really, but there's the water, right? Here's the dock.
You just want to use all your fancy.
I do, yeah, I do. I want to use I want to play with all my stuff here. So here, maybe we'll put the boat, right? Here's our boat. Okay, there's our boat.
Red flag. Red flag.
A red flag. Okay.
Do a blue flag.
White flag.
That's
Pirate
right.
flag.
Pirate flag.
Pirate flag.
Yes.
No, red
Jolly
flag.
Roger.
Honor
Jolly Roger.
Pirate flag.
Jolly Roger.
Hey, you gotta get the skull.
Yeah.
on the side.
No, this is just a plain black flag.
Baby
Anyway, there it is.
Okay.
There's a black flag. Okay, so it says that let's take this information one at a time here. The winch is 12 feet above the deck of the boat. Okay? So the deck of the boat is where? Well, looks like it's right there, right? Okay, that's the deck of the boat. We'll call that the top of the boat is the deck, right? Okay, so here's our dock over here then, right? And the winch is located, it's mounted up high. Who knows, it's on a pole or something, right? So we got this pole. And what's it say about the winch?
12 feet.
It's 12 feet above the deck of the boat. Okay, does that make sense? So here's our winch, and this distance is 12, and it's attached to the front of the boat, right? What's it tell us? What else do we know?
13 feet of rope.
Okay, there's 13 feet of rope, so we can put a 13 there, right? Okay. Although, I'm not gonna do that. In fact, I'm not gonna put any numbers on this for just a second. We'll come back and add numbers, but there's an important point I wanna make with this. You gotta treat these carefully. So this is our picture, right? Oops, there's our picture. Okay, we gotta,
I see what it's asking. Okay.
so we want to be able to describe this dynamic process, right? And we talked a little bit about this yesterday. Calculus is uber cool because it is dynamic, it's not static, right? It's not just that we've got this static picture where the boat is just sitting here, it's actually moving towards the dock, right? And normal math doesn't really allow us to do this kind of thing, but calculus does. So we need to attach some variables to this because the quantities are gonna change. So anything that's going to vary needs to get a variable, it needs to have a variable in the picture. So what are some things that are gonna change here?
The length of the rope.
The length of the rope. Yeah, so let's call that R, how about? Okay, so this distance we'll call R. What else is maybe gonna change?
Distance.
Yeah, the distance of the boat from the dock, right? That's horizontal, so let's maybe call that X. How about, okay? Is the height of the pulley gonna change? It's not. That's a constant, and so because it's a constant, we could put a number on there to represent that, because it's not gonna change. So that was 12. Does that make sense, what we've got? Okay, so and one other thing maybe we could, I'm just gonna I just wanna take this whole picture and move it to the next page. So one other thing I'm gonna do is I'm just gonna summarize that the rope is being pulled in at a constant rate of 4 feet per second. just so I can avoid having to have all the text up there. And what are we trying to find? The speed of the boat when there's 13 feet of rope out? Okay. So let me do this. Okay, so let's go through this process then. Can I make that a little bit smaller? You guys see that if I make that a little bit smaller? Like that? Is that good? Okay. Okay, so let's make this a little smaller. Let's put this up here. There's our picture, right? So now let's go through these steps. So we want to identify the snapshot value. So remember that this is like a movie, right? This is a dynamic thing. So in calculus, we got to think about the stuff we're doing in terms of a movie, right? It's continuous, changes in quantities. But we're asking about a specific frame in the movie, right? We're asking about the place where the rope is, where there's 13 feet of rope out, right? So the boat's going to continuously get closer and closer to the dock, but one frame in the movie is going to capture that moment when the boat has 13 feet of rope out, right? So we're going to call that our snapshot. That's the one frame of the movie that we're going to focus on. And we want to know what are the snapshot values of all the variables. So at that one instant in time, what are the things that we know? Okay? So what are some things that we know? So R is 13, right? So step one, we know that R is 13, and we'll just suppress the variables here. We'll just use the same variables the whole time. We're using feet to measure distance, and we're measuring seconds to measure time, right? Okay, what else do we know?
X is 5.
X, okay, we could solve for X, couldn't we? Right? We could solve because this is a right triangle, and this happens to be a 5, 12, 13 triangle, doesn't it? Right? And if you don't recognize that, you could just use the Pythagorean theorem. We could add some information that's not given to us directly. X equals 5. Okay? Okay, we know something else. We know something else here. We know the rate. Yeah. What's this for? We're pulling in rope at a rate of 4 feet per second. What quantity is that going to be? Yeah. Okay, that's got to be, now look at the units. We're going to use some dimensional analysis. Okay, it's obviously it's going to be, it has to do with the value of R. It's measured in feet per second, and so that's got to be a rate of change of R then, doesn't it? Right? With respect to time. Because R is measured in feet and time is measured in seconds. So for those of you that were gone yesterday, we added a little kind of a custom or something that we're going to fall back on to help us distinguish between special rates that are with respect to time. We've always said we could represent a derivative in a bunch of different ways. Like we could in this case, we could talk about this as being dr dt, right? Or we could call that r prime of t, or we could even maybe make a shortcut and say r prime. But because it's with respect to time, we're measuring a rate with respect to time. That's what we almost always do in physics, right? And these are physics problems. We're looking at this how system changes with time, because that is our most common quantity against which we're measuring change. We're instead going to call that r dot, right? So when you see a dot over a variable, it's talking about the rate of change with respect to time, okay, as opposed to something else. So we can say then that the other thing we know is that r dot equals what? No.
1 or 0.
No.
R,
R, 4.
4, R.
Before you,
Let's go back and look at this for a second. It says the winch is pulling in rope at a rate of 4 feet per second. So what's happening to the value of R?
Oh, it stinks. Oh,
Oh,
it's
it's-
getting smaller.
It's getting smaller. So then what does that tell you about the rate of change? So the rate, it's the rate of change of R. If R is getting smaller with time, what's that telling you about the rate then? It's negative. Yeah, because the value of R is decreasing, right? Think about this for just a second. Think about this in terms of if we were graphing R, the length of rope, as a function of time. What's that going to look like? It's going to look like this, isn't it? Right? Because the value of R is decreasing with time. Well, dr dt is just the slope of that line, right? Does that make sense? So it has to be negative. You don't have to draw that graph every time, but I think it's important to kind of always link your thinking to what it would look like in terms of a graph. It's very helpful. But what the big hint here is that the rope is being pulled in. So if the value of the quantity is decreasing, that means the rate is negative. If it's increasing, then the rate is positive. Okay? So R dot equals what then? What did we say? -4 standard units, right? Okay, so the snapshot variables, we wanted to do two things. We wanted to write all the stuff we were given, but also we want to write what we're trying to find. What is it that we're trying to find here? I'll go back to this for a second. First question we're asking is the speed of the boat. How would we measure the speed of the boat in that picture? Feet per second would be the units. Yeah. Speed's a rate, right? Speed's a rate, so it's the rate of change of what variable? X. Yeah, because isn't the boat moving horizontally? Right? It's floating, so it's moving horizontally. And so what we're looking for is X dot. Right? Does that make sense? That's the hardest part of the problem. And that's the coolest part of the problem, is that you get to actually take this situation and set it up mathematically. Right? Now it really gets a lot easier from here. All we're trying to do now is step 2 is we need to create a parent equation. So we've got to find an equation that relates the static variables in our snapshot, right? So, I mean, these are variables, but we're going to freeze them in our snapshot. And so you can think about this, if we just blur our calculus vision and ignore the dots, we want a static equation that relates all of the variables that are either represented by themselves or inside of rates, right? So it looks like we've got X's and R's. Well, look at that picture, and what's the relationship between X and R based on that picture? I mean, this could appear in different ways. It might be, it might be something that's geometrical. It might be, if it's talking about a particle moving along the path of a parabola, then maybe it's the equation of, it could be lots of different things, right? But I've just got to come up with a way to relate the variables X and R based on our situation. What's it going to be?
Cosine.
Well, okay, I can see why you'd say that, but if I talk about cosine, then I have to introduce another variable, like a theta or something. I don't want to do that.
Would it be R times all the X's equals on the dot?
Okay, it's not going to have any dots in it,
would they?
right? Because the parent equation is without dots.
Would they by chance be proportional?
That's what I was thinking.
Well,
Does that make
I'm
it
not going to
easier?
answer that. You tell me, and if so, why? But
Well, isn't.
so I will tell you, no, they're not.
No, okay.
Just so you don't waste time going down that road. But
Yeah.
there's something. I mean, just look at this. Kind of ignore all the specifics here. Just look at the picture. What do you know about that picture? What's the relationship between X and R?
It's both in the same direction.
Okay, but you're thinking in terms of rates. I don't want you to do that. The parent equation involves the variables included in the snapshot values, right? we're not gonna think about the rates themselves though. Ignore the dots. If you just think about just the static quantities, R represents the amount of rope out, and X represents the distance of the boat from the dock. Don't think rates.
They both have 12, so 30.
Well, okay, but what do you see there? There's something, you guys are missing something really simple here.
Right angle.
It's the right angle is critical.
Score.
What is this? Pythagorean theorem. Yeah, it's a right triangle,
But what
right?
is the 12?
X and R are just the sides of a right triangle formed by the rope and that, imagine that distance between the boat and the dock, and then the 12-foot pole that the pulley's mounted on, right? So what is that relationship in terms of a Pythagorean relationship then?
12 squared plus
R squared equals
12 squared plus
X squared.
X squared.
equals R squared.
Agree? That's our parent equation right there, okay? I know this, and you guys were thinking, like, okay, we got these rates in here, but remember, when you're coming up with the parent equation, it's gonna be sort of non-calculus stuff. All you're looking at now is, I just wanna find some relationship between those variables. Now, if we calculusify that, yeah, these are gonna be changing, and this triangle is gonna be morphing with time, right? This point is gonna be moving forward, so it's gonna change the values of the quantities X and R, but it's always gonna be a right triangle, isn't it? Right? That makes sense? And so this relationship is always gonna hold, okay? So now we've created the parent equation, now we're going to relate the rates. Okay, now we do calculus.
Re-rate.
Okay, we're gonna relate the rates by implicitly differentiating, right? So we've got the static equation. Now, we're just gonna implicitly differentiate with respect to what variable? T, because all of our rates are written with respect to time, right? So now what we wanna do is relate the rates by doing the differentiation, right? So what do we get then if we differentiate with respect to T? What does this first term give us if I differentiate with respect to T? 2x dot, right? Because I've got something squared. Well, the derivative of something squared is 2 times something. And the derivative of something with respect to T, not x, right? If we were differentiating with respect to x, we would just get 2x. But because we're differentiating with respect to T, when I look inside, the derivative of x actually gives us an x dot, right? What's the derivative of 12 squared? 0. The derivative of r squared?
2r dot.
Good, and then I could just divide each side through by 2, right? And there's I've related the rates. Now my last step is, I'm just gonna isolate the variable that I'm trying to solve for and plug and chug, okay? So which variable am I trying to solve for? X dot. So all I'd have to do is just divide each side by x. So I get x dot equals r dot over x. And those are all things that I know, so I can plug and chug. I can just plug in values now, right? So what's r? 13 looks like, right? What's r dot? What's x? So that's going to be our answer. So x dot is going to equal negative 52 over 5. So it's going to equal negative 10.4. And what are my feet? What are my units going to be?
Feet per second.
Feet per second. So that's how fast the boat is moving at that moment in time. Okay?
Well, wouldn't it be positive?
No.
In a sense of realistic, like if you were looking at that.
No, the negative is actually important, because what's that tell us about the boat?
It's going in a negative direction.
Yeah, because x is decreasing, so it's moving towards the dock. Okay?
If it was just a speed boat.
If we wanted to speed, then it would be
Yeah.
10.4.
Yeah.
Okay, what do you notice here though about what happens as the boat gets closer to the dock? How are we gonna know what's going on there? What's happening to its speed? R dot is constant, right? Everybody agree?
You can change R. Wait, you can change X.
We could change either R or X. Like if I wanted to, and this is kind of a cool question too. So we answered the specific question, but there was a kind of just a talking point at the end. What happens to the speed of the boat as it gets closer to the dock? Okay, what's going to happen? I just love problems like this. This is so cool. So here we get this answer, right? And we want to know, so what's X dot going to do as a function of X, how about, as it gets closer to the dock? So what I could do then is right now we got a problem because I've got R's and X's in there. But I could easily just go back up to my parent equation and say R is the square root of X squared plus 144, right? So then I could replace that and I'd end up with
Wouldn't it be
X
R-
dot
wouldn't it
as a
just be-
function of X.
Wouldn't R just be X plus 12? Or
No,
square
you
root?
can't do
Yeah,
that.
yeah, okay, yeah, makes sense.
And then times R, which is -4, right? So let's put that out front. But what's that going to do? What does the square root of X squared plus 144 over X look like? All we'd have to do is just look at that function, wouldn't we? Now we could graph this, right? Why don't we? Why don't we graph this as a function? So we've got X dot as a function of X there, right? So if I just pull up my calculator, because we want to know what's happening to the boat as it gets closer. So as X gets smaller, right? Okay, let's look. So we've got the function -4 times the square root of X squared plus 144 divided by X.
That doesn't seem right on the graph.
Are you sure? Zoom 6. Okay, so maybe let's go, we just want to look from, how about if we just go from, we'll just look for positive values of X. Let's let the window go from 0 to 10, how about? And I'm just going to go from -100 to +10, that's fine. So think what that's representing. It's representing on the horizontal axis what?
Or horizontal is the
Distance from the.
The X, right? So X is on the horizontal axis. What's on the vertical axis for our purple function there?
Time.
No. Look, I've got the function. The function is X dot, right? What's X dot mean?
that's the function rate of change.
Rate of change. So it's the speed of the boat, right? So we're graphing the speed of the boat as a function, or the velocity of the boat, we should say, right? The velocity of the boat, because it's negative, as a function of distance from the dock. So now I know why this didn't look right to you, because you were thinking about moving from right to left along the graph. But really all we're doing is we're exploring what happens as X gets closer. As X gets closer, what happens to the value of X dot? It gets bigger, just more negative, right? So out here, the boat is moving towards the dock relatively not very fast. What if I approached infinity? What if I went out infinitely far? As X approached infinity, what am I gonna get for an answer? How fast is the boat approaching?
It would eventually hit zero.
This is, we haven't really done this.
Like realistic.
It wouldn't hit zero because you would be small.
Would you get a, what's it called, a asymptote?
You would. You'd get an asymptote if I went really, really far out there. Now, we're gonna look at this next chapter. We'll look at a way to actually analyze, take this limit as x approaches infinity. I don't wanna get into that right now because there's a little bit of background that we'd have to talk about. But just think about the picture for a second. If we went out to where the boat was infinitely far away, what could you tell me about the direction of that line? As it goes really, really far away, what happens to, like, this angle right here? What's it going to approach? 90, right? Everybody agree? This line's going to become very, very close to parallel. Everybody agree? If the line were parallel and we're pulling in rope at a rate of 4 feet per second, how fast is the boat moving? If the line is parallel to the surface of the water, 4 feet per second, right? Everybody see that? You can even kind of just see it graphically. As the boat approaches an infinite distance, this line approaches being parallel, right? And so then all of the rope that's being pulled in is pulling horizontally, right? And so the boat would have a speed of 4 feet per second. But look what happens as x gets closer to the dock. That's no longer the case. And then it turns out that x dot actually gets quite a bit bigger, right? And so this is probably not a good scenario if it's your boat. It's just going faster and faster as you get closer to the dock, right? Okay, that make sense?
But this problem doesn't take into account like the brakes on the boat.
Well, no, you're right. I mean, this is just, but it's valuable information to know. I mean, you know, it's,
Same thing, leave your winch or your boat.
there you go, right. Okay. What time is it? 11:05, we got a little time?
10 minutes.
Okay. You wanna do another one or you wanna work? I don't care. Might as well just do another one, huh? Just practice a little bit, cause then you guys can work.
Computer left for 3 minutes.
Yeah, you can have tomorrow to work then. Let's do another one. Now, isn't that cool though? Isn't that, to me, that is just, I love that stuff. I mean, that's where math becomes real. You know, math has always been really contrived in the past, but calculus makes it real because it's dynamic and the world is dynamic. Let's try another one. Let's see, another one I think is a really good one to do because it has an important point would be one like this, okay? So, you guys, as I'm doing this, you can even maybe start to draw a picture.
Same example.
Did I spell conveyor right?
Good.
Yeah.
I know what you mean.
Actually, comma between belt and onto.
Say it again, comma.
Between belt and onto.
Oh, maybe. This may not be grammatically correct.
That's like,
Whoops, of the. Okay, there it is. That's a good one. So we need a picture, right? Pretty simple picture. What's our picture gonna look like? Cone, right? And so when you're drawing a cone, really, we might as well just draw the cross-section of the cone. Everybody agree? There's no reason for us to get fancy and make this all three-dimensional here. We're just trying to get a picture that we can work with so we can get some variables in this, right? So there's our cone. What variables are we gonna probably use for our cone? So we could say x.
D for diameter.
Okay, well, we could, yeah. How about instead of diameter, how about if we use the radius? We'll call it x, right? Because ultimately, thinking ahead a little bit, we're gonna have to come up with a parent function, and this is probably just gonna be a geometric formula, right? So we'll call this distance right here x, and we'll call that y maybe for height. Does that seem reasonable? Okay. So in terms of those variables, what are we given here? What's one thing we're given? Okay, yeah, we're given the height, aren't we? So we're told that, for step one, we're told that h is what? 15. And we're gonna be consistent with our units, so we won't worry about the units. Distance measured in feet, time measured in minutes, right?
Our dots.
Okay, what else do we know?
Our dots 10 cubic feet per minute.
Okay, now what about that 10? Yeah. What kind of rate is that? Cubic feet per minute.
Acceleration.
So what's cubic feet? So the minute's obviously a t, right? It's gonna be a rate. It's gonna be a dot because we're measuring with respect to time. But what is cubic feet a measure of? Volume. Yeah. So that's actually a v dot, right? V dot equals positive 10 feet cubed per minute, right? So once again, we'll just leave the units off. Okay. That's really all we're given. What are we trying to find?
The
The rate of
rate of height.
So yeah, so we're trying to find how fast is the height changing. So what's that going to be? H dot. Good. Okay, so step two, we need a parent equation, right? So our parent equation is just the volume formula in this case, right? So we know that the volume of a cone is just 1/3 pi r squared h. So for us, r is x, right? So x squared y. Okay. All right, now, do you see an issue there? Yeah, we've got information about, I called it h. I meant to call it y, didn't I? Better fix that. Right. I called that h, but we didn't call it h. We called it y. We're given information about x, or about y and v, but no x's.
We need so it'd just be
But
x
it
equals 3h, or divided by 2,
3y.
or 3y.
Okay,
but-
yeah, so we're gonna need a secondary equation here. We're gonna need some other equation to relate the x and the y. But they give us something, don't they? They tell us the base of the pile is approximately 3 times the height, right? So we could take this statement and we could turn that into the secondary equation. The base is just 2x, right? That means the diameter is equal to 3y, right? Everybody agree? Okay, there's a couple things we could do here, and I want you to really pay attention to this, because this is a very strategic thing. Calculus is nothing if it's not strategic. Our next step is going to be to relate the rates by implicitly differentiating, right? Okay, that looks kind of nasty, because we're going to have a product rule there, right? Wouldn't it be better, being as I'm given information about y, and I'm asked about y dot, but I'm not asked anything about x, nor am I given anything about x, wouldn't it be better if we could just take this parent equation and we could rewrite it in terms of y only? Did you see the benefit of that? I'm not going to go through to demonstrate how foolhardy it would be to just differentiate. I'd have to go through the whole process of differentiating this thing. Would you agree, though, that if I did that, I'm gonna end up getting X's and Y's and X dot and Y dots in a complicated, expression, right?
Yeah.
And then we'd have to go back and figure out, okay, so now when Y is 15, I'd have to add an X up here, right? And I'd have to maybe find out what X dot is, and that's a big process. But how about if we just do this? If we want to eliminate the X in favor of a Y, doesn't that mean we just isolate X, right? So we could come down here and say X equals 3 halves Y, and that's our substitution equation, and we just plug that in, right? Now look what that does. That makes this otherwise kind of a hard problem. We're now able to write V as
Wait, what?
pi over 3 times, or I'm just combine those, times X, which is 3 halves Y squared. Right, because that's just my X times Y. That's no big deal. So that gives us, what are we gonna get? We're gonna get a 4 on the bottom, aren't we? And we're gonna get a 3 on the top because one of those cancels one of those, right? So we're gonna get 3/4 pi Y cubed. Is that right? Check my math. That seem right?
Is that just for simplifying?
Yeah, but now look what we got. We got Y, or we got V as a function of Y only. That's great. Now our calculus gets a lot easier, right? So now when we relate the rate, so we go to step 3, it's pretty simple, right? We just, I've got V equals this stuff, right? So on the left side, I'm just gonna get a V dot, right? On the right side, I've got this constant out front. What do I get if I differentiate this with respect to T? I can ignore that for a second. That's just out front.
3y, y dot,
Yeah, I'm gonna have 3
y squared.
out front, so 3 times this is just gonna give us a 9/4 pi Y squared times
Why don't?
Y dot. And that's what we're trying to find, right? Okay, and so then, if we wanna solve for Y dot, step 4, well, you get the idea, right? But did you see the important part of that?
Yeah.
Was relating those variables, eliminating a variable?
It's just the
Okay.
substitution thing.
Can you, request?
Yes, I can.
Oh, same